Hey everyone, and welcome. All right, so today let's dive into the pretty fascinating world of the robot operating system, or as you'll hear it called, ROS. It's kind of the invisible brain and nervous system that powers so much of modern robotics, and we're going to break down just how it all works. When you see one of those incredible, complex robots, maybe it's a Spot Dog from Boston Dynamics, or a surgical robot, or even just one of those smart vacuums, have you ever just stopped and wondered, how does it do that? What's the secret sauce that lets all those different motors and sensors and cameras work together? Well, the answer, it's a little more complicated than you might think. It's not just about writing one big chunk of code. The real magic, the really hard part, is getting all of those individual pieces to have a seamless, continuous conversation with each other. In this really puts the scale of that challenge into perspective. I mean, just imagine trying to be the conductor for an orchestra of hundreds, maybe even thousands of different parts, all needing to talk at once, all needing to be perfectly in sync. That is the fundamental problem that robotics engineers are always trying to solve. So the first big swing at solving this problem was a platform called ROS1. And the goal was simple but ambitious: create a common language, a standard way for all these different robotic components to talk to each other. And look, for a long time, it was an absolute game changer. ROS1 gave developers this incredible head start. It came packed with libraries and tools, and this huge community jumped in, building and sharing all sorts of useful packages. All of a sudden, you didn't have to be a massive corporation. A small team could build something incredibly complex without starting from scratch every single time. But for all the amazing things it did, ROS1 had this critical flaw, kind of hiding right in plain sight, one that made it a really tough sell for a lot of real-world mission-critical jobs. Okay, this diagram really shows you what I'm talking about. See that central hub there, the ROS master? In ROS1, every single message, every piece of communication had to go through it. It was the traffic cop for the whole system. And you can probably see the problem. If that master fails, the whole show stops. The entire robot just dies. It was the definition of a single point of failure. Yeah, and this quote just hits the nail on the head. It wasn't just the single point of failure. ROS1 also had a really hard time on unreliable networks like Wi-Fi, and it had basically zero security built in. And look, if you're in a research lab, maybe that's okay. But if you're building a commercial product that people are counting on, no way. It was a total deal breaker. So, what did they do? The whole community basically went back to the drawing board. And this wasn't just some little update like a ROS 1.1. No, this was a ground-up redesign. They called it ROS 2, and it was built from day one for the demands of the real world. And wow, the difference is just night and day. You can see it right here. On the left, you've got that old ROS 1 architecture with the master right in the middle directing traffic. But on the right, with ROS 2, it's just gone. Now, all the components discover each other and talk directly. It's a decentralized, peer-to-peer system, which is just way, way more robust. And hey, that was just the beginning of the upgrades. ROS 2 was built on this industrial-strength communication standard called DDS, which, is a fancy way of saying it's super-duper reliable. It also works on Windows and Mac OS now, not just Linux. And this is a big one. Security was baked in from the start. This thing was finally ready for prime time. Okay, so how does this whole new conversation actually work? Let's get into the nitty-gritty, the actual grammar of how robots talk in ROS 2. It really boils down to just a few core ideas. All right, so the most basic building block, the atom of the ROS universe, is called a node. And the easiest way to think about a node is like a tiny, hyper-focused employee. It has one job, and it does that one job really well. You'll have one node to read a camera, another to control the wheels, another to plan a path, and so on. And look, you don't have to be a coder to get what's going on here. Whether it's written in Python like on the left or C++ on the right, the big idea is exactly the same. You're just making these simple, modular, self-contained little programs. It makes the whole system so much easier to understand and to work on. Okay, so you've got all these nodes. How do they talk to each other? Well, the first method is called topics, and the best way to think of a topic is like a public chat room. One node, called a publisher, is basically shouting out updates to the whole room, like, here's the latest camera image, here's the latest image, and any other node that cares, a subscriber, can tune into that chat room and listen. Let's see what that looks like. So you've got node A, he's the publisher. He's just sending out, hello. over and over to this topic, this chat room. And node B, the subscriber, is tuned in, so it hears every single one. And the cool thing is you could have a node C, D, and E all subscribe to that same topic, all getting that same info at the same time. But okay, broadcasting is great for sensor data, but what if you don't want to shout to the whole room? What if you just need to ask one specific node a question and get a direct answer back? Like, hey, what's 2 plus 2? Well, for that, you've got services. It's a direct one-to-one call and response conversation. And what's cool is you can have a bunch of different nodes or clients, all asking questions of one single dedicated service provider. Like, imagine a node whose only job is to calculate the distance to a wall. Any other part of the robot that needs that info can just call up that service and get a quick, reliable answer. Super efficient. All right, so we've got broadcasts for continuous data, that's topics. And we've got quick Q&A, that's services. But what about the really big jobs? Like, hey, robot, go from the living room to the kitchen. That's not a quick question, right? That could take minutes. For that kind of task, we have something called actions. They're built for long-running goals, they give you feedback along the way, and importantly, you can cancel them. And this is where it gets really clever. Actions are basically a hybrid. They're a mashup of the other two. They use a service-like model to send the main goal, go to the kitchen, and to get the final result, I'm here. But in between, they use a topic to send a constant stream of feedback, like, okay, I'm 25% of the way there, now 50%. It really is the best of both worlds. So, to really nail this down, let's put them side by side. Services are your go-to for those quick fire-and-forget tasks. You ask, you get an answer, done. You can't cancel it halfway through. But actions, those are for the long haul, the big missions where you need to know what's happening every step of the way, and you might need to say, hey, never mind, cancel that. Okay, so this is all great, right? We have nodes, topics, services, actions, a whole language for robots. But think about it. A really complex robot could have hundreds of these nodes running all at once. So how in the world do you launch all of that at once and make sure everything is configured and talking to the right thing? It sounds like a nightmare. The answer is actually super elegant. It's something called a launch file. A launch file is basically the script for the entire performance. In one single file, usually written in Python, you describe the whole robot's software system. You say which nodes to run, what settings they need, and then you type one simple command, ROS2launch, and boom, the entire orchestra starts playing perfectly in sync. So really, by solving this fundamental communication problem, ROS2 didn't just build a better system, it created a whole new, robust language for machines. It's the foundation that the next generation of robots is being built on. And that kind of leaves us with this one big, fascinating question to think about. Now that these machines have a proper language to speak to each other, what are they going to say next?